Welcome to the Convex 2.3 solutions. In this part, we'll be discussing the third problem, that is PCPS. So the main problem is we are given an array and we have to find the number of ways to split the array into non-empty contiguous parts such that each part contains at most m distinct values. Now, in this question, first we have to figure out how we can find a contiguous subarray that contains at most m distinct values. So we can do that using a technique called sliding window. So let's see how it works. So suppose n is the yeah. So suppose n is the size of the array and we maintain a frequency map. This map tells us that a particular element has appeared this many number of times. Now we maintain two pointers, that is high and low. So we iterate our high pointer from 0 to n minus 1 and we increment the frequency uh, of the value present at the high index by 1. Now what we do inside the while loop. So this loop says that till the size of the map is greater than m, that is, if there are more than m distinct elements in this map, then we increment our low pointer and we reduce the frequency of the element which is currently present at the low pointer. And if the value goes to 0, then we delete this element. Now, when we reach this point, then we are sure that the subarray from low to high, both index inclusive, contains at most m distinct values. This will be useful for further calculations. If we think about smaller subproblems, then we can solve this problem using dynamic programming. So suppose we are currently at the index high, and suppose low is the index which is found by the sliding window algorithm. That is, the subarray low to high contains at most m distinct values. Now suppose we maintain a DP state where DP of I indicates the number of ways to partition the array starting at the index 0 and ending at the index I. Then our answer will be DP of n minus 1. Now let's see how we can calculate this value. So suppose we want to find the DP value at high and we already know all the previous values. Now since this is a subarray that contains at most m distinct values, so we can consider this subarray as one part, and then here, since we know the value of DP at low minus 1, so DP at low minus 1 basically indicates that the number of ways to partition the entire array from 0 till this index. Now in all those ways, we can add this one single part, since this is a valid part, and now we can increment this pointer. So this is also a valid part, because since if this bigger subarray contains at most m distinct values, then this smaller will also contain, and so on. So in all those ways, we can add this as one single part and calculate the answer for the DP of high. So the formula for DP of high becomes DP of high is the sum of DP of low minus 1 from low minus 1 to DP of high minus 1. So from DP of low minus 1, that is here, we take the sum from DP of low minus 1 to DP of high minus 1. This gives us our DP of high. And this works because all the smaller subarrays of this entire array will contain less than equal to m distinct elements. So here is the code for the PCPS problem. So first we take the inputs, the n and the m, and then we declare an array of size n, and we make a DP of size n, and we also maintain a DP sum, which basically denotes the sum of all the DP's values from 0 to I. And this is the mod constant. Now we take the input. Now, as discussed earlier, we maintain a frequency map, and we make two pointers low and high. And when we come here, so at this place here, we are sure that the subarray from low to high contains at most m distinct elements. Now, suppose if the high is 0, that is, if we are at the first index, then we have only one element. So we can partition the entire array in only one way. So the answer is 1. Now, if let's say the starting point of window is 0, that is, if low is 0, then what we can do is, so as discussed, we can sum up all the DP values from 0 to high minus 1, and then we can take the entire subarray from 0 to high as well. Therefore, we add 1 for this also. So this is the formula for that. Now, the DP sum from 0 to high minus 1 can be found directly in constant time using this DP sum array. Now, if the value of low pointer is greater than 0, then we take the sum from DP of low minus 1 to DP to high minus 1. So basically, this DP sum array, which stores the sum from 0 to I. So we take the subarray sum using this formula, yeah, so so from the sum to high minus 1, we reduce the, we subtract the sum till low minus 2. And then we update our DP sum. So DP sum is basically the previous DP sum, which is the high minus 1, and the DP sum at high. And then we output the last value of the DP. Now the time complexity of this program is order n, because this low and high pointer, so this high pointer runs from 0 to n, and the low pointers at max can go to n, and we are adding values in the hash map and removing values from the hash map, which takes order 1 time. So this entire loop, so this entire inner loop for the entire run of the outer for loop will run only n times. Now if we come to this step, so this step is order 1. This one is also order 1. This step is also order 1. This step is also order 1. So the time complexity of this program is order n. And regarding space complexity, so we make 3 arrays, each of size n, and we also maintain the frequency map. So all these takes order and space complexity.